Hi, this term, the first chapter, chapter 1, is the sequences and series, and now I want to summarize the first section of this chapter, which is the sequences of real numbers, where first we will start with the definition of a sequence. You already see that a sequence is a function whose domain is the set of natural numbers and the range is the set of real numbers. For representation of a sequence, either parentheses or curly brackets are used. In this course, we will use curly brackets. If you note here that in between curly brackets, a sub n is given, which equals to a set with some elements a sub 1, a sub 2, a sub 3. The index n here takes positive integer values. Sometimes, in fact, it can be 0. But for simplicity and without loss of generality, we will take the initial value of n being equal to 1. The elements in the set a sub 1, a sub 2, a sub 3 and so on are called the terms of the sequence, where a sub 1 is the first term, a sub 2 is the second term, and a sub n is either called the nth term or the general term of the sequence. Now we may look for some examples of the sequences. Example 1, 2 and 3 gives almost the same type of examples, but if we continue with example 4, in this case, if you note here that a sub 1 is 1, a sub 2 is 1, and a sub n plus 2 equals to a sub n plus a sub n plus 1. That is, this is an example which is different than the first three. But then we can say that a sequence can be given or specified in 3 ways, where I also want to say that the last example that is already seen here is called the Fibonacci sequence, where we specify the sequences in general in 3 ways, either by listing a few terms or by providing a formula which is the general term of the sequence, or recursively, that is by a recursion formula. But in this case we have to define a finite number of terms of the sequence, where in the example a sub 1 and a sub 2 are defined, that is given values. Since a sequence is given as a function similar or analog to the properties of the functions, sequences also has some properties, where now I want to mention about 2 basic properties. One of them is the boundedness property, and then I will talk about the increasing decreasing property. But if we consider the boundedness property, we are saying that a sequence is bounded below if all terms of the sequence are larger than some number n. That is, no element or term of the sequence can be smaller than n. The opposite condition gives us the bounded above position or the property. In this case we are saying that if all terms of the sequence are less than or equal to a number m, then it is bounded below. If both of those conditions hold, means if it is bounded below and above also, in such a case we are saying that the sequence is bounded, where generalized definition of this form is given in the last line. The second property that we want to mention about is the increasing decreasing property. In this case we are saying that if a term is larger than or equal to the previous one, then we are saying the sequence is increasing. If the inequality is reversed, that is, if a term is smaller than or equal to the previous one, then we are saying that the sequence is decreasing in this case. And if either it is increasing or decreasing, in such a case we are saying that the sequence is monotonic, where this definition can be put in two different forms, where it is called the monotonicity test in this case. That is, either we may write an plus 1 minus an, which can be larger than or equal to 0, or less than or equal to 0. In such a case, we are saying it is either increasing or decreasing. Or if all terms of the sequence are larger than 0, then we can consider the ratio of an plus 1 over an, whether larger than or equal to 1 or smaller than or equal to 1. And again, in such a case, we are saying the sequence is either increasing or decreasing. If we consider the example n over n plus 1, in such a case, if you note here that all terms of the sequence are larger than or equal to 0, means that it is bounded below. And also all terms are smaller than or equal to 1, it means that the sequence is bounded above. So we are saying that the sequence is bounded. On the other hand, if you consider an plus 1 minus an, in such a case, this difference equals to 1 over n plus 1 times n plus 2, which is smaller than or equal to 1. That is, the sequence is decreasing. But also, we can say that an plus 1 over an, the ratio, because all the terms are larger than 0, where this ratio in this case is smaller than or equal to 1. So in such a case, again, we can say that the sequence is decreasing. That is, both criteria which are given in monotonicity test can be used for this example. Monotonicity test gives result explicitly for the sequences whose general term is a simple expression, like the previous example. In general, to get the result whether a sequence is increasing or decreasing, for complicated expressions of the sequences, we define a continuous and differentiable function f, and using the derivative of this function, we can say whether f is either increasing or decreasing. And depending on that, if f is increasing, then the sequence is increasing. If f is decreasing, then the sequence is decreasing. If we want to use this property for the example of the sequence n over n squared plus 1, in this case we can define the function f of x, which is x over x squared plus 1, where the derivative of this function is smaller than or equal to 1, means that the function is decreasing. So we can write the conclusion that the sequence is also decreasing. Another important property for the sequences is convergence of the sequences, where this is something like the limit of a function as x goes to infinity, where since a sequence is a function, we can talk about the limits of the sequences as n goes to infinity in this case, where if this limit exists, we are saying that the limit, the sequence an converges to the limit value l. If limit does not exist, we say that this sequence diverges. In general, we won't write for those limits n goes to infinity. Instead of that, we will write limit an equal to l, because there is no other possibility for the limit point, and always should go to infinity. For the simplicity, we may not write it. The words converges and diverges are the verb form of the convergence, but also we can use the words convergent and divergent. So we can say that a sequence is divergent or a sequence is convergent. Now we can apply this definition to the example 1 over n, and using the definition we can show that the limit of the sequence 1 over n is 0. That is, we can find a capital N which is larger than 1 over epsilon. So if we know what epsilon is, we also know what this capital N is. Certainly in the lectures you will find some more examples related with this topic. Now we have two useful theorems for the limit. One of them is the limit of the function f. If f has a limit L as x goes to infinity, then we know that the limit of the sequence an is also L. The second theorem gives us some properties of the limit, such as linearity, multiplication, ratio, multiplication by a constant, or ordering of the limits. Then one of the useful and well-known theorem is the squeeze or the sandwich theorem for the sequences, which is also given for the limits of functions for the general case. After all those, we want to mention about one more important topic related with the sequences, which is in general not given in the calculus books, that is called the subsequences. By saying a subsequence, we mean that it is a new sequence obtained by deleting some terms of a given sequence, and the definition is already given here. What is the use of it? In general, we use the subsequences of a sequence for the convergence of the sequences, or maybe to show that it is divergent most of the time. But one of the basic ideas is that, which is given by the theorem, if a sequence converges to a number n, then any subsequence of the sequence converges to the same number. But on the other hand, we are saying that as a corollary, if any two subsequences of a given sequence an converge to two different limits, or if one of them or both diverge, then the sequence an diverges. So this is a very useful corollary, because sometimes it may not be easy to show that a sequence diverges, but if we can find two subsequences which satisfy the conditions, one of the conditions of the corollary, then we can say that the sequence diverges. Increasing and decreasing properties of the sequences and boundedness also can also be used to show that a sequence converges. In this case, there can be two steps. One of them is if a sequence increases and it is bounded above, then we say it is convergent. Or if it decreases and bounded below, then it is also convergent, where this test or theorem is called the monotonic sequence theorem. And by this theorem we complete the review of this section. Next review will be series. Goodbye.